Hello everybody. In this mini lecture we are going to look at the left exactness of home functors. As you know, there are two kinds of home functors, namely the covariant home functor, which keeps the direction of your morphisms, and the covariant home functor, which turns every arrow around, every morphism around. And for both of these there is a lemma saying that they are left exact. So I'm going to prove one of them, which is a little bit harder, and I'm going to leave the other one as an exercise for you. So I'm going to prove that the contravariant home functor is left exact. So this is written in this lemma here, which is in this black box here. So suppose we have a sequence, an exact sequence. By the way, we're talking about modules here. You may think of your own category as long as the arguments I'm going to use fit in this category. So we have a long, an exact sequence, not a long exact sequence, an exact sequence of modules. From this module m bar, we have a morphism v going to m and a morphism u going from m to m double bar, and from there we go to 0. And we want to apply the contravariant home functor. Remember, for every a module, we get such a contravariant home functor by sending such an object m double bar, for example, to a set, namely the set of morphisms from m double bar to n. So this is a functor going from the category of A modules to the category of sets. For every object, for every module, you get such a home set. And you map morphisms. So for instance, this morphism going from M to M double bar to morphisms in the category of sets. So in other words, to set theoretic maps, simply by precomposing. So if you have a morphism going from m double bar to n, you precompose this with f to get a morphism going from m to n, and this is what this morphism u star is. You can view this as a pullback. We want to prove that, that this sequence that we get from applying this contravariant home functor to our original sequence is left exact. So what does it mean for this sequence to be left exact? What do we need to check? We need to check that since we have a 0 here, this one, u star, has to be injective. And we have to show that the image of u star is the kernel of v star. Okay, well, let's start with discussing injectivity of u star. Well, that's easy. Suppose you have a morphism. Suppose you have two morphisms, let's say f and g, which are both morphisms from m double bar to n. We have to show that u star maps them to different morphisms from m to n. But look, u is is surjective by exactness of our original sequence. So if you have these two morphisms f and g from m to n, and you precompose them with u, for them to be the same, they have to agree on every point, because u is surjective. This is in a nutshell why u is injective. I won't even bother to write this down, since this is really easy. The other easy thing is to show that that the kernel of V star contains the image of U star. The image of U star looks like this. Have a look at this diagram here. We have morphisms going from m double bar to n, and we precompose u, as I have mentioned, and this gives us a map from this set of morphisms going from m double bar to n to the set of morphisms going from m to n. But we have exactness here. So the image of V is the kernel of U. So if you have such a composition of F with U, and you precompose this with V, you get zero morphism because of this. V and then U is 0 because the image of V is the kernel of U. So this proves that the kernel of V star contains the image of U star. And to show the other inclusion, we need to do a little more work, but it's also not hard. We're again using surjectivity of U. What do we need to do? We need to say that for every h in the kernel of V star, so we have a morphism h going from m to n, and we assume that this h is in the kernel of V. So V precomposed h is a zero morphism, and we have to show that this implies that h is in the image of U star, which is the same as saying that there is a morphism F. So there exists a morphism F going from m double bar to n, such that precomposing this morphism by U gives H. I have sketched the proof here. Since this morphism U is surjective, we have a pre-image for every element in m double bar. So let's look at a particular element which I have called x double bar. So x double bar is an element of m double bar, and we want to define what this morphism F does to this element x double bar. So this is surjective, so we can look at the pre-image U inverse of X double bar, and then we can apply H, and then we have a morphism F that does what we want to do, but we have to check one thing before we are done, because the pre-image of X double bar might be a set with more than one element. And we have to check that this definition of F is well defined. So suppose we have two different elements in the pre-image of X double bar. I've called these two images A and B. So since they are both in the pre-image of X double bar, we have that U of A is equal to U of B, which is equal to X double bar. But since U is a homomorphism, this means that U of A minus B is 0. So A minus B is in the kernel of U, but the kernel of U is the same as the image of V. So there exists an element X bar inside M, such that V of X bar is equal to A minus B. So we can write this as A is equal to V of this element X bar plus B. And then we can apply H, and we see that H applied to A is the same as H applied to V of X bar plus V plus H applied to B, but H applied to V of X bar is 0, because we have assumed that H is in the kernel of V star, which is the same as saying that precomposing H with V, which is what we have done here, gives 0. So indeed we have H of A is H of B, and this proves well-definedness, and this concludes the proof of the left exactness of the contravariant home functor. Thank you for watching. If you liked this video, please don't forget to like and subscribe. See you soon.